On Halloween, which is 10/31, I ran some testing and we notice the smoke control system is working because we have very short peaks of opacity, very few over 20%, and we have a quick resolution or correction to bring it back in line. This is also a good comparison of the corrected color shift versus color shift and the temperature of the sensor. You can see between 2 hours and 7 hours that the temperature of the sensor was up near 90, and that created a color shift of approximately 20 um, nanometers. And then when we apply the color shift correction, which is dependent on a temperature change, it comes right back in line. And it's I mean, you can see where I put fuel on and that it quickly overcame the smoke and got it flaming again. So this is a really good chart. It also shows that, when we get out 24 hours, opacity drops to just about zero and the color shift settles into something close to zero. This is the appearance of the octoring with the green light in it. I do think that everybody would see this as a green light. It's a narrowband green light, so it does produce quite a bit of incident light. I can run it up to like 450 without overloading the sensor, 450 lux. And it does have color shift. So as the system is working, it does offset from its native green. It also reports in at around 1 to 200 nanometers, which is not typical green light. The manufacturer says this is right in at 550 nanometers. However, it's confusing for the light sensor. It does produce a consistent value. However, it's just not the value you would expect. So this is the green octoring out, a night photograph with a star. So this is 10 hours of the same data set on Halloween. And you can see, I'll have a shorter one, so I won't talk about the very beginning here. You can see that there's a color shift when we have a high sensor temperature, which I've come up with a mathematical correction, and that's the yellow line that brings it back into around 10 nanometers. You can see clearly that whenever I put fuel on, we have a quick spike up, and the control system takes over and gets it flaming again, and the opacity drops. So that's all real good. There's only like 1 or 2 data points over 20%. So you can get a good clear view here of the corrected and the color shift and the opacity. When I'm training people how to change light sources and align the sensor, this is the green light. And you can see I have the hottest portion of the light at the center and an annular ring around the port. This allows us to get the brightest light through the port. So this is the inside of the octoring with the light being projected onto the sensor side of the octoring with a hot spot that is centered on the port. All right, here we are with the first 2 hours of data. I did have a tough time getting this fire going. You can see for the first hour, I was wrestling with it, and the opacity went really high. That's someone who puts a lot of fuel on and expects it to burn. Well, it just wasn't ready for it. So we have a fairly high opacity reading up to 90, and then the control system kicks it into flaming mode, and we have some color shift as well. But mainly what we see in this stage of the fire is opacity or blocking of light through May scattering, excuse me. However, then we get the interaction of the color shift. About 1.5 hours, we have more of a color shift corrected signal than we do of opacity. So 2 hours of data kind of shows that I had a tough time getting it started. We had a high opacity event. We were putting a lot of smoke out for a few minutes, and then it got under control, and we're back off to heating the house again.